A tunnel worth $10 trillion connecting New York to London sounds like pure fantasy. Yet for over a century, visionaries have chased it as the ultimate symbol of human ambition. Imagine shrinking the Atlantic to a 1-hour ride, rewriting how continents connect. It is not real. The world's leading experts are still left speechless by a single question. Why does this impossible idea refuse to die? And how close could we ever get to building it? The fantasy of crossing the Atlantic in a single seamless leap has always captured the imagination. For generations, the idea of a tunnel stretching from New York to London has promised more than just a shortcut. It is a symbol of what humanity dares to dream. In a world where a flight between these cities takes 7 hours, the concept of arriving in just 60 minutes feels like science fiction made real. The tunnel stands as a monument in the public mind, a bridge not only between continents but between what is possible and what could be. People imagine waking up in Manhattan and sipping tea in London before breakfast. They picture families, business travelers, and artists making the Atlantic crossing as casually as a subway ride. The tunnel becomes more than infrastructure. It is a vision of a world where borders shrink and cultures blend at the speed of thought. This is the appeal that refuses to fade. It is not only about travel, it is about rewriting the meaning of distance and time. Megaprojects have always fascinated, but the Transatlantic Tunnel sits at the very edge of what anyone can picture. It is the ultimate test of ambition. A single structure uniting two of the world's greatest cities and promising to redraw maps, economies, and daily life. The idea has inspired magazine covers, television specials, and endless online debates. Each new generation rediscovers the dream, layering new hopes onto the same bold line across the ocean. At its heart, the tunnel is a mirror for human aspiration. It asks how far we are willing to go, what we are willing to spend, and how much we are willing to risk to bring the world closer together. The fantasy persists not because it is easy, but because it is just barely imaginable. That tension between the limits of today and the promise of tomorrow is what keeps the dream alive, no matter how many times reality intervenes. Ideas as bold as a tunnel under the Atlantic do not appear out of nowhere. The roots of this vision stretch back more than a century, surfacing again and again in the minds of inventors, engineers, and futurists. In the late 1800s, the world was already gripped by the promise of railways and steamships. That is when the first whispers of a transatlantic tunnel began to circulate, not just in novels, but in the technical journals and patent filings of the era. Michel Verne, son of Jules Verne, imagined a vacuum tube train connecting continents as early as 1888, weaving the concept into the fabric of science fiction long before the technology even existed. By the early 20th century, figures like Robert Goddard, better known as the father of modern rocketry, were sketching out patents for intercontinental tunnels. Goddard's curiosity pushed the boundaries of what people thought machines could achieve, and his name became tied to the idea that the impossible might only be a matter of time. Across the Atlantic, German novelist Bernhard Kellermann published Der Tunnel in 1913, and its later film adaptations brought the vision into the public eye, fueling debates about whether such a feat could ever move from page to reality. The dream did not fade with the decades. In the 1960s and the 1970s, as humanity reached for the moon, new generations of engineers revisited the tunnel concept. Swiss professor Marcel Juffer outlined a transatlantic link, while American physicist Gerard K. O'Neill became known for audacious megastructure ideas, space habitats, and lunar colonies. O'Neill did not focus on tunnels specifically, but he embodied the era's appetite for thinking at planetary scale. Every so often, the idea would leap from the drawing board into the mainstream. In 2003, Discovery Channel ran an episode of extreme engineering that examined the tunnel. And in 2004, Popular Science described a vacuum maglev system that could, on paper, cross the Atlantic in under an hour. Each wave of interest brought new technologies into the discussion, from superconducting magnets to deep-sea robotics. Magazine covers, television specials, and online forums kept the tunnel alive as a symbol of what might be possible, even as costs ballooned from billions to trillions in each new round of speculation. This ongoing fascination is not a fluke. The tunnel's pedigree runs through generations of dreamers and doers, each returning to the same question: can engineering shrink oceans the way it once shrank continents? The record shows a lineage of thought experiments, not secret blueprints. This is a story of ambition measured in kilometers, decades, and the willingness to imagine beyond the horizon. New York to London. On a map, the line stretches nearly 5,500 kilometers, about 3,400 miles, straight across the Atlantic. That number alone is hard to grasp, but set it next to the world's longest undersea tunnels, and the scale becomes almost surreal. The Channel Tunnel, linking England and France, runs just 50 kilometers beneath the English Channel. It is considered a modern engineering marvel, the product of decades of planning and billions of dollars. The Gotthard Base Tunnel in Switzerland, the world's longest rail tunnel, measures 57 kilometers. Even the Seikan Tunnel in Japan, burrowing under the sea for 54 kilometers, does not come close. Now imagine a tunnel more than 100 times longer than any of these records. A path so vast it would cross an entire continent if laid out on land. The distance from New York to Los Angeles is about 4,500 kilometers, still 1,000 kilometers short. The transatlantic tunnel concept dwarfs every infrastructure project humanity has ever attempted. This is not just a matter of length. The tunnel would have to traverse the continental shelves near the coasts, then plunge into the deep ocean basin, where depths reach 4,000, 5,000, even 6,000 meters. The pressure at those depths crushes steel and concrete as easily as a boot crushes an eggshell. For nearly the entire 5,500 kilometers, there would be no exits, no stations, no surface access, just a sealed tube in the silent blackness beneath the Atlantic. A length comparison graphic tells the story. The Channel Tunnel, a thin bar at one end, the Gotthard and Seikan tunnels, barely longer, and then, stretching far beyond the screen, the transatlantic concept, an order of magnitude beyond anything on record. The numbers are so large, they strain the imagination. This is not a tunnel you walk through or even drive through. It is a structure that would have to survive century after century, battered by forces no engineer has ever faced at such a scale. The sheer distance is the first and most obvious challenge. But as the tunnel leaves the shallow continental margins and enters the abyssal plain, the true perils begin. Depth, pressure, and the unforgiving geology of the ocean floor turn an already impossible distance into a gauntlet of hazards. Beneath the Atlantic, the ocean floor plunges into a world almost entirely hostile to human engineering. As the tunnel concept leaves the safety of the continental shelves, it faces the abyssal plain, a vast silent expanse where water pressure can exceed 500 atmospheres. That is more than 7,000 pounds pressing on every square inch, enough to crush steel and concrete in seconds. No existing tunnel has ever been built at these depths. The Channel Tunnel, for comparison, sits just 50 meters below the seabed in calm, predictable geology. Here, at 5,000 meters, the rules change completely. The geology of the Atlantic is a patchwork of hazards. The route from New York to London would have to navigate steep slopes off the continental margins, cross the flat but treacherous abyssal plains, and skirt the mid-Atlantic ridge, a tectonic boundary marked by earthquakes and volcanic activity. Sediment layers shift with every tremor, and fracture zones like Cane and Romanche can offset the seabed by hundreds of meters. In some areas, the crust is young and unstable, riddled with hydrothermal vents and volcanic ridges. In others, ancient sediment blankets the ocean floor, hiding pockets of gas hydrate that can destabilize the ground without warning. Pressure is only the beginning. Materials that survive for decades in shallow tunnels would corrode, crack, or collapse in the deep. Every kilometer of tunnel must withstand not just the crushing force of the ocean, but also the slow, relentless attack of salt water, shifting sediments, and the chemical stew of the deep sea. Repairs would be almost impossible. Even undersea cables just a few centimeters wide require specialized ships and robotic submersibles for maintenance. A tunnel large enough to carry trains or capsules would multiply every challenge by orders of magnitude. Oceanographers studying the abyssal plain describe it as one of the least explored environments on Earth. There are regions along the proposed route that have never been mapped in detail. As Dr. Helen Ramirez, a marine geoscientist, has pointed out, we know more about the surface of Mars than the geology 5 kilometers below the Atlantic. The risks are not just technical, they are fundamentally unknown. The sheer depth and unpredictability of the Atlantic floor would force any tunnel project to rely on autonomous construction. Human crews cannot survive the pressure or isolation. The tunnel would need machines capable of operating for years without direct intervention, enduring conditions no robot has ever faced. Each meter bored into the seabed would be a step into darkness, uncertainty, and risk. These are not just engineering problems, they are frontiers that have never been crossed. No tunnel of this scale has ever been built, and the reason becomes clear the moment you consider how it would actually be constructed. Human crews cannot survive the pressure or the isolation beneath thousands of meters of water. That leaves only one option: machines working alone deep below the Atlantic for years at a time. Today's tunnel boring machines, called TBMS, are technological marvels, but they are designed for land or for shallow water, not the crushing depths of the abyssal plain. Even the most advanced TBMS, like those used for the Channel Tunnel or for urban subways, require constant human oversight and support. There is no fully autonomous TBM that can dig for hundreds or thousands of kilometers without direct intervention. Supplying a machine in the middle of the Atlantic would be a logistical nightmare. There are no mid-ocean staging points and no way to send workers or spare parts to a TBM that could be hundreds or even thousands of kilometers from the nearest land. Power, ventilation, and waste removal would all have to be managed remotely, with no margin for error. The materials themselves would face a hostile environment. Salt water, high pressure, and shifting geology would attack steel and concrete relentlessly. Over a century or more, corrosion and material fatigue would threaten the tunnel's integrity, demanding maintenance operations at a scale never attempted. Geotechnical engineers who study these challenges often point to the gulf between what is possible on paper and what is possible in practice. In an interview, Dr. Marcus Lee, a tunnel engineer, explains, "We can automate certain processes, but a fully autonomous machine capable of boring through the unknown geology of the deep Atlantic, repairing itself and handling emergencies without human intervention, that is science fiction right now. The supply chain alone would be a showstopper. Even if a TBM could be built to survive the pressure, the logistics of keeping it supplied and operational over 5,500 kilometers of hostile terrain are unsolved. Every kilometer adds new points of potential failure. Material fatigue, especially at joints and seals, would accumulate over decades, with no easy way to intervene if something goes wrong. The deeper the tunnel, the more isolated the machine becomes, and the less room there is for error. The dream of a transatlantic tunnel runs headlong into the reality that, for now, no machine exists that can build it, and no supply chain can keep up with what it would demand. A tunnel stretching under the Atlantic is not just a question of digging or distance. The real test comes the moment something goes wrong. Imagine a sealed tube 5,500 kilometers long, running deep beneath the ocean. If a fire breaks out or a train stalls, there is no exit for thousands of kilometers in either direction. In the Channel Tunnel, emergency exits are spaced every few hundred meters. For a transatlantic tube, the nearest escape could be 2,000 kilometers away with 5 kilometers of water pressing down from above. Rescue teams cannot reach the midpoint. Even sending help from either end could take hours or even days. Now add speed to the equation. The promise of a 1-hour trip from New York to London means traveling at nearly 5,500 kilometers per hour, faster than a jet fighter, deep underground, inside a vacuum. At those speeds, the physics of stopping safely become brutal. A sudden halt or depressurization is not just inconvenient, it is catastrophic. A breach in the tube would unleash a shock wave, equalizing pressure in seconds, with no way to isolate or reach affected sections quickly. Maintaining a vacuum across such a distance demands flawless seals and constant power. Any failure, mechanical, structural, or human, could strand passengers in a lifeless environment with no air, no light, and no rescue path. The faster the system, the higher the risk. Every promise of speed multiplies the danger, and every safety measure adds cost and complexity. For now, the operational realities of evacuation and survival make the tunnel less a marvel of engineering and more a warning about ambition outpacing caution. Cost is the first wall the transatlantic tunnel hits, and it is not a small one. Even the most optimistic estimates put the price tag in the $15 to $20 trillion range, and as engineering details pile up, so do the zeros. The Channel Tunnel, at just 50 kilometers, cost about $25 billion in today's dollars. A tunnel 100 times longer, passing through some of the harshest conditions on the planet, would send costs into territory never seen before. Maintenance, energy demands, and century-scale upkeep push the total higher still. On a cost scale, the tunnel does not just break records, it creates an entirely new category, far beyond any infrastructure project in history. But even if every dollar could be found, there is another barrier money cannot clear: the law of the sea. Most of the tunnel's path would cross international waters, where no single country has authority. The United Nations Convention on the Law of the Sea provides rules for cables and pipelines, but it does not cover a permanent inhabited structure for passenger transport. There is no legal framework for who would own the tunnel, who would be responsible for safety, or how emergencies would be handled when disaster strikes far from any nation's reach. Maritime law scholars point out that unlike undersea cables, a tunnel would require entirely new rules that do not exist and that would take decades of negotiation to create. The environment weighs in as well. The construction and operation of a tunnel this size would disturb deep-sea ecosystems that are still largely unexplored. Sediment plumes, noise, and chemical leaks could ripple through food chains, stretching from the ocean floor to the surface. With so much unknown about these fragile systems, the risk of unintended damage is impossible to ignore. This tunnel is not just a test of engineering or imagination, it is a collision with the limits of international law, financial reality, and environmental caution. Even if the technical barriers could be solved, the world would still have to answer who pays, who governs, and who takes responsibility when things go wrong beneath the Atlantic. Right now, the Atlantic remains uncrossed by any tunnel. Its vastness a reminder that some frontiers resist even trillion-dollar ambition. But every new engineering vision raises the bar for what is possible tomorrow. As technology advances and global challenges demand bold solutions, the real test is not the price tag. It is whether we dare to imagine at this scale. The limits we set today shape the world we inherit next.